Hey, welcome back to another coding session. Continuing as always with Bangalang. Our, what's the thing I always say? It's a low-level, explicit, compiled procedural language that runs on the CPU and GPU. We've got the core of the language working. We're just running through a bunch of features now to round everything off, and a bunch of cleanup and bugs. So we kind of have an end in sight. Or at least, once we've done this whole list, I feel like I can actually use the language to do some other projects. Last time we did procedure defaults, I believe, default parameters for procedures, which is very nice. And then I was thinking to follow it up with default struct members. But I've put it down the bottom here with a question mark now because I'm a little bit unsure if that's the way I want to go. Because right now, if you declare a variable with no value like this, it's by default, basically, it's the same as this for everything, which means that everything is all zeroed out. And if we put defaults for struct members, that kind of makes things a little bit more complicated, because then it's like this for non-structs, but for structs it's something different. And I don't know, somehow consistency here feels simpler to understand. So I'm going to think about that a bit longer. We'll put that on the back burner. And right now I wanted to go for this one. This one I think would be quite nice. Array and slice literals. So at the moment we have struct literals. I don't know if I have an example in here. I think definitely in Broomstick we have a struct literal, so this guy here. So this is a struct type, and we're assigning this here, which is our struct literal. So it's curly braces with a bunch of assignments in it to assign the members of the struct. Very nice. But now I want to have this kind of thing for arrays and slices. So I think what I'm going to do for testing is just basically let's just comment everything out and have some really simple stuff. So foo is a I83. And what we want is to be able to do this, right? And I guess we can have the OS import, so then we can do os.exit. I think I have to cast it to, I think it's a U8 actually. So if I go foo 0, we should get some sort of error. Yeah, here we go. Parsing error. So we need to allow this. So that's a change to our grammar to begin with. So this I'm still going to consider it a compound literal. Or could there be like two different? That's a good question actually. So this is our compound literal, which can have a sign which is like, to be honest, I feel like this is way too permissive, having assignment here. I think I would prefer, like identifier equals like right-hand side expression, maybe. So that it's more restrictive. Or identify equals statement would also be okay. So if that's an assignment, yeah, I'm wondering if we should really worry about that right now. So So let's not worry about that right now, and I'll sort of show what I want it to do. So that would be something like this. So I just wrapped that in extra brackets, right? So there's an extra set of brackets. So then I can put, ooh, wait a minute. So then I can put an or here, and we can do another thing, which is, I'm going to say right-hand side expression for now, because that'll make it easier. That does mean that if we wanted to do a struct literal and it was like an array of procedures, we couldn't define the procedures in place. We can't do that anyway because we don't allow anonymous procedures, but that is something we want to support later on. But anyway, so within our curly brackets, we've got this or here. We can either have what we had before, which was one or more assignments separated by comma, or now we can have one or more right-hand side expressions separated by a comma. Those are the two options for a compound literal. So in our parsing of a compound literal, this is something I'm slowly changing as well so that it matches the grammar better. Let's just say if length of children is greater than 0, then we need a comma first. So that eliminates the trailing comma, for better or worse. That's what I'm going to do for now. And instead of parse, okay, so we can parse an assignment. I think here we need to have this pattern where we can say like member assign, well, I did a bad job spelling that, assignment node, member assignment, okay, and we also need a member assignment stream, which is the main stream, and then we pass that guy in. What's wrong with that? I think I put that on the wrong side. And then we do the same thing with the right-hand side expression, which I think does not need a context. But now let's say expression for all these variables. So this is kind of like what we do for statement. So there's all these ones that are obvious because they start with a keyword, but then there's this ambiguous, we don't know what kind of statement we're going to get until we start parsing it. So here again, let's get the next index from them so we know. So this max next index tells us, like this next index we can use to tell how many tokens did we get to while trying to parse this thing. And the one that we got furthest with, that's the one that we say we actually use, right? So then you get something like this. I'm not sure which one would be best to use, but let's say we do this one. If the assignment parsed more, so the trick is like if they parsed exactly the same amount, then what do we want to call it? I think actually we want to call it an expression, because both an assignment and an expression could be just a left-hand side. It could be just an identifier. That would be valid for both of these, I believe. So we want to, I think, prefer this one. I really do want to nail this down better though, actually. Now, more thinking about it more, this is way too permissive to say like any kind of assignment could be in a compound literal. It really should be more restrictive than that. But we'll come back to that. Okay. So we update the stream and return the node. We might not have parsed it successfully, but we still say that that's what we used. But we're not actually returning here. I think we're just saying that we're adding it as a child. Yeah, because we're looping through, right? So otherwise, and it's not the stream, it's the node. But if it's not okay, then we want to return false, right? So if expression, if it's not okay, then we return. We say, look, couldn't do it, couldn't do it. And this one is for the assignment. So this is assignment stream, assignment okay, and assignment node. So that's all well and good. We can have either of these in this loop, but then the extra consideration is that it should be either all assignments or all expressions. So I want to record if so let's say assignment members and expression members. And if we come into here, as soon as we come into here once, then we say, look, we're doing expression members. Or if we come in here, then we're doing assignment members. And if we're doing expression members, then go into here. Is that right? Because then, say we did an expression member first, and then the second time we come along, this one wins, but it comes into here and tells us what's wrong with the expression because that's what it's expecting. I think that seems all right. So do we really need this? Maybe it's better to do a negative thing. So if that wins and we're not doing assignments, then come in. Yeah, I'm not sure about this. I'm not sure this is really giving me what I want. Because here, still, if we do an expression first, so assignment members remains false, then we come around, assignment wins. Now let's say assignment wins first. So we go here, and then next time expression wins, but we don't go in here because we're doing assignment members. So then we go here. Okay, yeah, that makes sense. So then what's the other case? The other case is that we do expressions. So we come in here first. And then if the next time an assignment wins, we come in and we still come in here. Yeah, I feel like I want to do the condition differently. So like, So I think I want to say like expression is when well, maybe we want to prove that it's an assignment. That seems to be what we want to prove. So if that is greater than that, then it's assignment. If expression members but if we have done this, if we've got either of these, then assignment equals assignment members. So for the initial one, it should use whatever we've parsed more of to tell whether it's an assignment or not. But then afterwards, once we have chosen one of these, and only one of these could be chosen, then we decide based on the assignment members. I think that's right. So then if assignment, we do this, otherwise we do that. Okay, I think they should work. I don't really like it somehow. It feels not great, but I think it should work. So I think that should be our parsing. So now type checking. And here we don't have, so this is something I've been wanting to do for a while actually. We don't have a compound literal file. So I want to split that out. Compound literal, and we'll just do the compound literal case, that's this one, down to here. Okay, yeah, type check compound literal, and then back here, when we have the compound literal case, we call type check compound literal, which is something like this, I guess. Beautiful. Okay. And now we want to change this because we want to allow, can only contain assignments. That's not true anymore. You know, to prevent these kind of checks, I think really I do want to restrict this. I think it's going to make our lives a lot easier. I do think that I think it's best to have an accurate grammar so that the parser can take care of as much as possible, because then later on it just makes our lives easier. So we want an assignment. I was thinking that we could make like a simple assignment. I don't know how useful this is, like if it's going to be reusable or not, but I'm going to say a simple assignment can go here, which is not a left-hand side expression. It's also just an identifier on the left, followed by equals, which is not optional, and then a statement. So it's really simple. Yeah, identify equals statement, that's it. I think that's perfect. The statement is more flexible than it needs to be. But here, since we have right-hand side expression, this is really not going to conflict, because right-hand side expression cannot have an equals. So I think that's going to work pretty well. So let's go back to parsing. Assignment, let's make a simple assignment. And So instead of a left-hand side expression, I said it's just an identifier on the left. I guess we'll keep this. We don't have to check whether it's a member or not because it's just an identifier. Instead of checking for any kind of instead of checking for any kind of token, we can just say like token type, oops, is equals. That's the only kind of assignment operator we support. Oh, okay, yeah. So we still do need to do it like that. So then there's our operator node, and the right-hand side is a statement as before. Oh, and this is not optional. This is not optional, that's right. So I think actually we just go like this. Nothing is optional, so equals that. Okay, there's our simple assignment, and then our compound literal, we say simple assignment. Does this need the context? Yes, because we're parsing a statement. Okay. So we parse a simple assignment now. Okay, great. So now in type checking, I already know that we've got like our correct stuff, so we don't have to say like, this was all here because assignment was not strict enough. See, what is it saying? Like, can only contain assignments, only assignments to members. So what that's saying is like, it has to be just an identifier. That's kind of what it was getting at. And there's one down here. Compound literal can only contain assignments with right-hand side expressions. We've said with the simple assignment that it has to have a right-hand side, so that's covered. These are not good. This should be type name when we're printing a message. That's type node. Oh, actually, no, this one shouldn't be, because that's not, whoops. Let's copy. That's not printing a type, but this is printing a type. Whenever we print a type, we should use type name. Okay. So it seems we need a child LHS node, which we do not have anymore. I guess we got rid of it. Oh, it was here, just within the loop, like that. Okay. All right. So struct slice. So these are like member things when we're looking for members. I think we'll just support arrays for now. So like if, we'll just start with arrays. So if we're looking at an array, well, first let's say like, you know, because now we can either have assignments or right-hand side expressions. So if we come across, if our child node is not an assignment, and it's not, and we're not an array here, we're not looking at an array, that we're creating the literal for, that's an error, because everything needs to use assignments except for arrays. So let's say, cannot use compound literal with type, cannot use with values for type, and then we'll say with assignments. So that's more, yeah, I feel like that's more descriptive. And then we can say, okay, so if we do have an array, I think I'm going to leave this for now. Yeah, we'll leave that for now. So if we do have an array, what are we going to do for type checking? Well, in here we made sure that they were the correct members, and we gave them type information. I guess here they're right-hand side expressions. So, we've already got the child node, so I think we should type check a right-hand side expression with the child node. That's what it is. A right-hand side expression. We're going to have to pass in an expected type. So the expected type, I guess, is the child of this type. Like this type is an array. And if we get the child of that type, maybe even just to make it more clear, and say child type node. Let's put it in here actually. So that should type check it. But another thing that we need to make sure of is that we have the correct number of values. So if we go back to here, we don't need that. Go back to here. So we could do like this. That should be invalid because this count does not match that count. And we should be able to check that. So we can say otherwise if, maybe just say otherwise, and so how do we get the array length? That's the second child of this type node. Well, I think that can be, no, that only makes sense for arrays. That's why I put it in there. But again, we're at an array, so it's like, this is the length, child 1 is the length. For an array type, it has two children. The first one is the type of thing that it's, the type of each element in the array, and the second child is the length. So here's the length, and here's the children. So these are like the, boom. So if these are the children, then I want to say if length of children does not equal length, that should be fine, shouldn't it? Oh no, because that's a string, so we need to strconv a to I, like so. And that's actually the value of that. Yep, okay. So now that we have that, we can say compound literal for type must contain X elements, we'll say. So that would be length. So let's leave our example with 4 so that should get caught. We could also do like bar is a struct, so then this should be invalid because this is a struct. So that should get caught up here. Okay, so we've made sure we have the right amount of values. We've type checked all the values. We've made sure that we only do this kind of compound literal for arrays and not for like structs and other things. Structs and slices right now. So I feel like that's good type checking. We should get some, ooh, I feel like that shouldn't have caused an error. Type check compound literal, so this is getting, yeah, so this left-hand side stuff is really geared towards this kind of stuff here. So maybe I'll say like, let's put that back there for now, but let's say if it is an assignment, then we make sure it's the correct type. We make sure it's the correct length. And then we do our type checks. Otherwise, we come down into here and do what we did before. Yeah, so we've got a big if else based on whether we're talking about assignments or not. So this is when we're not assignments, we go into here. Yeah, we make sure it's an array, we make sure it has the right length, and then we do the type checking. So then this child business only makes sense here, because this left-hand side is for an assignment. So let's try that. Cannot use compound literal with values for type. Missing argument. Oh, I thought I had fixed that. Okay, yeah. I think I have fixed it in the past when I was playing around with stuff, but I guess I never did it when I was recording. In types, we have this type name. This type name stuff, and we need to, like, whenever we have a curly brace, I think we need to escape it. I don't know about this one. Maybe that one too? Yeah, so then we get what we thought. So cannot use compound literal with values for type struct. Yeah, because that's not allowed. So that was this one here that we didn't allow. Now we should see that it has the wrong length. Compound for type, so that should be compound literal for type must contain 3 elements. Great. So we push it back to 3, and then we get an error in generation, which makes sense because we haven't done anything in generation yet. Okay. But I think that type checking is pretty good. So let's go to generation. generation, we'll do it for both actually, because one of the main things that I want to use this for is this here. This has always annoyed me that we have like all this to like declare our vec4, and I would rather just have a literal right here. Could be just a one-liner, you know. But getting back to where we were, again, I'm going to make a compound literal file. And let's find the compound literal case. Here it is. And there's the bottom there. Like so. I think probably some parameters it doesn't need. I don't think it really cares whether there's allocations or not. But the rest it does need. We need a type node as well. So we go back to primary. Compound literal. Generate compound literal context node register num. But we want the type node, which I guess is declared way up here. Cool. Now that we have that split out, I'm going to turn this into a switch. Maybe in we might change it to switch in type checking 2. So switch on the value. And then we're going to have just, instead of this, it'll be case struct. This will be case slice. And this will be the default case. There's an assertion. And because I love my ordering, let's put it in alphabetic order. And let's put the array up top. So it was failed to generate primary. So yeah, it was probably, oh, this should probably be compound literal now. It was probably this assertion because it tried to generate a compound literal and it didn't have the array case. So what are we doing here? I guess we want to get the, so we've just allocated our array. So the array, and then we want to like, I guess loop through all of the expressions. Yeah, and generate them. So it's kind of like this, I guess. But it's actually the, no, it's the, this node has children and each child node is an expression. So we don't need to do this. So we get the expression, we put it, we need to put it somewhere with a type. And the type is the child type node. Again, so let's go child type node dot children 0. So this is the type of the element in the array. That's the type. Each expression in the literal should resolve to something that is the type of the thing we're putting in to the array. So now we just need to know where to put it. Well, we've just allocated the array. So yeah, here we go. This is the location. So this is, let's call this element location this time. So we want to put it there, and each time we want to move forward in the array. So we're going to, well, we need to add to the offset. And I guess we can say like element size. Maybe it's even clearer actually say element type. Yeah, that's clearer. So that's 2 byte size, and I think give it the type node. And that's what we want to add each time. So that should write the correct memory to fill this array we've just declared. Let's try it. Okay, that's not a good sign. Looks like we've gone into infinite recursion, which is never good. So what kind of node are we talking about here? An array type node. So compound literal. Ah, yes, I think I know why. For the same reason that in type checking, you'll notice that we do this. We cut off the last child because the last child is the type, and we don't want to mess with that one. Yeah, I think also in this case, we shouldn't really be looking at the type node. So let's do the same thing. And go children, like so. Try that again. Finish with exit code 1, which sounds bad, but is that what we expected? Foo0 is 1, so if we go foo1, we should get exit code 2. Beautiful. Foo2 is exit code 3. Beautiful. Okay. And let's just test again, like if I do that, it should say wrong number. And also if I go too short, it should say wrong number. Cool. Right, now to kick things up a notch, what I also want to do is support slices here. So this is going to be a bit trickier because a slice is just a pointer to the data and a length. So we need to actually store the data somewhere. And I think what I'm going to do is store it in a static variable. So let's see, I guess let's put these in order. Let's go back to type checking. So to start with, let's allow slices. Or maybe we can do something similar, like down here, right? We have like struct slice, and then let's turn this into a switch. I think that might actually be clearer. Switch on this. Like that, and so the struct case is to do this. The slice case is to do that. And this is the default case, is that we have an error. And again, I'm going to put the slice above so that it's in alphabetical order. And yeah, and this happens for all cases. So that's great. And now I want to do something similar up here. So this is where we have this error to say we used the wrong type. And to do the length check, Well, I guess the length check only makes sense for an array, right? We could put as many elements as we want in here for a slice, and we're just going to dynamically, well, the compiler is going to create this array, so it doesn't need to be a certain amount. So this type checking is array specific. I feel like we're always going to want to do that. Make sure that our member is the right type. So for slices, is there anything we need to do actually? Maybe not, just that. Let's say do nothing, I guess, at this point. Yeah, let's leave it at that. And then we go ahead to generation. And so for arrays, we know we do that. Or maybe again, we'll do 2 switches like we did before. So I guess actually the tricky thing is that for slice, no, that's right. The parsing makes sure that we have only values or only assignments. So at this point, we don't need to worry about that. Okay, great. I thought we had an issue, but we do not. So now if we're not talking about assignments, we do one thing, otherwise we do another thing. So this here is for this. And let's put an assertion on the end of this one just in case. Okay, that condition is going to have to get a bit more complicated, but let's just say there's no arrays for this part. Arrays are only when there's not assignments. Further down the road, we're actually going to add some members, but let's not get into that right now. So if length of children is greater than 0, because at this point we don't know, it could be empty. Here we're already in the loop. That's interesting. Do we want to do that here as well? No, there's different kinds of loops all the time. Yeah, so we can't really do that here. So if we have children and the first child, the type of the first child is not an assignment. So we're not talking about assignments. Let's go. I mean, if the length of children is 0, then there's no point in doing anything, right? That's a point. We should probably have a case where if the children is 0, we just return like nil or something. We just nullify. That would be more efficient. I'm going to put that as a to-do. Nullify for empty compound literals, because it feels like something I don't want to do right now, but we should do. Okay, so this is how we take care of arrays. How do we take care of slices? Yeah, so that's right. We need to create an array like this, but this array needs to be a static variable. So Context.program.static vars equals, I guess we're going to have to create an AST for it, and we need to give it a name. So I guess we need to start with the qualified name of this procedure. So we get the qualified name with the path. So we need to import program. So now we have the qualified name, and then we say like the static var name is like a concatenation of qualified name with, what else do we need? Probably like a dot array underscore and then an index. So I guess we need to get like an index from the context. So there's our index. Actually, that's right. I prefer this. It's a nicer syntax because now I can just do %s %i like that, and it will complain a lot because I put an extra comma in there. Okay, so that's our static var name, but we need to create our static var node. So the static vars, I think they're assignments. Let's go to our generation. Yeah, here's our static vars. So we get a static var node, which needs to have a left-hand side. Yeah, so it should be an assignment, and we only care about the type node of the left-hand side, basically. It needs to evaluate to the correct size. Okay. So we have an assignment, doesn't have a value. Let's append to the children. So we're creating our left-hand side node, which it wants. Oh, that should be type equals. So that's identifier. We don't really need to give it a value, but why not? We have the value here. And then this, the left-hand side needs to have a child, which is the type. So the type is the array type. So I feel like it's this type node. Ah, no, this is a slice, so that's not going to help. So we need to create a type node, which is an array. And that needs to have two children. The first child is the type of the element. So element type node. I think we can just put element type node like that. And then the second one is a number, which is the length. So again, I'm going to do this because it's easier and I'm lazy. So this should be length of children, I guess. Children is what we're going to loop through. Yeah, that's the amount of things that's in the literal. So that's how long we want the array to be. That's a pointer, so we need to dereference. Okay, so hopefully that should create the correct static variable with the correct size. And now we want to say that that's what we, do we need to return something here? Return copy stack address. Yeah, I feel like that's still right. You know, now we are, because what we want to return is the slice. So we have created a static variable of the right size, and it's at this point that we fill it out. Because our static variables are a bit weird. It's when we execute this line that we actually like populate the values into the static variable, and then we assign the static variable over to here. So now we need to do that assignment. So I guess it's kind of like index. Where's index? This is the index stuff. Where's the slice stuff? Here it is. So it's kind of like this. This is our slice address and slice length. Yeah. So we need to do something like this. And the length. Okay, this length is like calculated, so that's a bit more complicated. I think we can just do a copy to the length. Okay, so the address location is it memory? I'm not sure if I'm going to get this right, but I think this is an immediate. Is it memory here? I guess we'll find out if these are wrong, because it won't work. And this, I don't know, reference type node. I think this is, I think I have an index type node, which doesn't feel quite right because it's actually a length, not an index, but they should have the same type. A bit messy, but so that needs to have the length in it, which I said was this. So that's also an immediate with the length. Okay, what happens? Exit code 3. That sounds right. Let's have a look at the code. Probably should check the code for an array as well. I think this is it. So yeah, allocations and deallocations are quite inefficient, but we allocate twice. This is where we have this double dot, which is kind of annoying me. So we have this static variable, which we declare down here. It's 3 bytes long because our array is 3 1-byte integers. So that's right. Then we assign our 1, 2, 3 into it. Then we copy the address of it to here. Which seems to work. And then I think this is kind of, oh no, we don't do the exit yet. So what the hell is all this stuff? Oh, this is doing the length. So this part here is creating our slice. This is the pointer to the actual data. This is the length. This here is doing a copy. So it takes a copy of RSP into R12. So this is now the location of our slice. Then it sort of deallocates that slice and then copies that slice to this other allocate. Like it's not great. If we just allocated once, then we could avoid all of this also, and that would be so much better, but we'll get there. And then this here is what we call exit. Okay. So I just want to see what the, if we do that, if we make that an array, what do we get then? It's this. So yeah, now we allocate 3 bytes directly here, we fill them, and the rest is all this stupid, that same kind of stupid copy stuff that we don't actually really need. So yeah, this is much simpler. I guess you would prefer that if you can. But that's cool. That's cool. So now I want to uncomment all this. Where are we at? Oh, I didn't set a timer. Oh, we're at an hour. Okay. Well then, fingers crossed that this actually works. Okay, so here's, we're running on the GPU, we've got GLSL. So this is where I actually wanted to use it. So now we could just do this, right? Let's cut out a whole bunch of code. Let's run that. And it crashes because this is on the GPU and I don't think we implemented that yet. That might be why. It seems we have like an infinite loop again. Expression primary. Well, this is the default case, right? What is our node type? Add a sign. Why is that being treated like an expression? That's weird. Program. Generate statement. Right-hand side node is an assignment. And the right-hand side child node we can't get. But the right-hand side child node is this one, which is our add assign. So why? Because it's not wrapped in a scope, and this is expecting it to be wrapped in a scope. It's expecting this to be a scope. Yeah, so actually one thing I thought that we could do, it is a bit weird, like many things that I do, but when we have an assignment and we're type checking, we have this bit here. So this is kind of to handle whether it's a scope or not. This is wrapping in a return if we need to. So I thought what we could do is kind of say, all right, if it's not a scope, wrap it in a scope so that we have consistency. All of our procedures have scopes, and then type check it like it's a scope. And that means that also when we get to generation, it's simpler, like where we were, where is it here? We can assume that it's a scope now. Where was I? Here. So this is the scope node. And it's scope. So we create a scope node. We add our right inside node as the only child. And then we'll replace right-hand side with that. Okay, let's try that again. Okay, this is what I expected. Compound literal is not defined. So I think what we can do for a compound literal, and apparently this will work for like structs as well. Maybe because we don't have that much time, we won't handle structs. So let's again, like we did, let's get rid of a bunch of these files so I can see what I'm doing. That's where we are. So when I did this type check, this generation, we did that. So let's do that again. Maybe we'll make a compound literal file actually. And then we do this to check whether we're dealing with non-assignments. And then we'll just say we don't handle assignments yet. But for this one, I think what we need to print is the type name. So that's, do we have a type node? No, it looks like we don't. I don't know if we need it again, so let's just put it like that for now. So we need a type name. Do we need anything else? We do, so let's go like this and say CJS, because we need a bracket. Basically, we're making like a constructor looking thing. So this is going to say like vec4 bracket, and then we need to loop through all of our children. And print them out as expressions. And we need to put commas. So let's say index, and if index is greater than 0, then we need to print comma space, like so. Then we generate expression. So that should be everything. And then on the end, we put a closing bracket. That should be a nice constructor. Does that work? Doesn't look like it. Oh, it's just going very, very slowly. It does this occasionally. I think maybe my recording audio might break up when it does that too. Let's try again. There we go. So that worked. I'm really surprised that my first attempt at writing that just worked. Okay, I know we're at an hour 8, but I want to tempt fate. I know that this is going to cause issues because I will get into it soon. But we have it working on the GPU. What about on the CPU? And here we see panic out of bounds. And this bug I have found while I was playing around, and it took me so long to figure out. So let me know if you do want like videos where I do spend ages trying to figure out bugs, but I feel like it's not the best content. So I'm going to try and run you through what's going on here. If I do this seemingly silly line, it works. And if I take it out, it does not work. And the reason that I tracked it down, because inside this bang, let me try to explain it properly. Inside bang, we have this loop, which enqueues things into the thread pool. And then in the thread pool, yeah, this is how it enqueues. It adds it into this array of tasks, and then it signals to say, okay, one of my workers, please perform the task. And what the broomstick should do is it should enqueue 8 of these things, 1 for each worker, and then wait for them to all finish. The problem is that this Futex business in Linux, this working variable needs to be 32-bit aligned, I figured out. And if it's not, then it doesn't work. And it doesn't wait. So it just comes around to the next iteration of the loop and keeps putting more in here until this task overflows and we get index out of bounds. So we need to fix this wait. We need to make sure that this working is aligned to 32 bits. And the reason that this weird change I did here where I added a string made it work is because when we go to the bottom here and look at all our static variables, here's our pool, because this, and for Boomstick, this is the pool that we use. So, and the pool is the, the thread pool is the thing that contains this working variable, this thing that needs to be 32-bit aligned. And we just make it a static variable, so it ends up down here, and we have no idea what the alignment is. And sometimes we just got lucky and it worked. But right now it doesn't work. I went back a whole bunch of commits. It hasn't been working for ages, but we never test on the CPU anymore. So we need to align this to 32 bits. I figured out that if we align the whole thing, then this is also 32-bit aligned. Luckily, that makes it easy. So what I'm going to do is I'm just going to create an align for directive. I would like eventually to have something like this, align equals 4, so we could just put whatever number we want. But for now, just to keep things simple, we'll say align 4. And hopefully this should make it so that when we declare the when we create the static variable, we can add some alignment code, because you can in here add some alignment, some things to make sure they're aligned to a certain byte. That's why I said 4, because it's 4 bytes, 32 bits. So if we go to generation of a program, and we're at our static vars. So in here, what I want to do is say, like, if, I guess we need to get our type node. Well, I guess it's the LHS type node if we want to be specific. And if that is a line 4, I guess, so what we're doing right now is we're adding it to a type. This is a type alias, so the type is going to have it. But you could also have variables, I guess, that have a line 4. So why not say LHS node could also have that directive? So if either of them have that directive, we want to print out align that number. And that number is, well, it's always 4, isn't it? So it's just align 4. Like so. There. What happens if we do that? It's not happy that we put that there. I think we don't allow directives for declarations. Okay, so we need to change that. So a declaration can optionally have a directive at the start. Not the declaration, the thing that goes on the left-hand side of a declaration can have a directive. Okay. Added parsing, left-hand side declaration. So it might be before the identifier. Do we have an if? Yes. So if we find a directive first, well, we wanted to have it on that node. So let's say directive is empty. Node.directive is directive get the token, you can go like this and get the value from the token, which is a directive token. So if we find a directive, we get the value from it, put it in here, and then put it on the node. It's a bit of a roundabout way of doing it, but that should give us the directive. It looks like it didn't print it. So I guess somewhere it's getting, well, let's just make sure that we put it right there, hey? So directive is untyped. Untyped. Align 4. Okay. So align 4 is getting added to this type. It must be getting stripped off somewhere, I guess. So this line is a type alias. So that happens in statements. Here's our type alias code. So we assign the right-hand side to the left-hand side, and the right-hand side does not have it. I guess we could do like this, right? Maybe we should do it like that. I mean, what happens if we do that? Then it works. Yeah, then we get our align 4 and it works. And we didn't have to make any grammar changes or anything. That kind of makes more sense, actually. I think that makes more sense. So maybe we'll undo this stuff. Undo that, undo this grammar change. Okay, but that's pretty sweet. That's pretty sweet, right? That now we can just do this. That's so much nicer. I do also want to eventually enable swizzling. So you could have a vec4. This is a taste of the future. Should be able to do like XYZ. And that should take the first 3 elements and make a vec3 from it. Or it could be XZY, you know, it could be XXX, like this. And that would make a 4-element array. I think maybe I'll limit it to 4, no more than 4. Or you could just do X and just get the single element. Odin supports that. I want to support that too. I've got a comment for it, but we'll do that later. But for now, I'm happy that we got this, and I'm happy that we squashed this ridiculous bug. I did see it crop up ages ago, and I investigated it and then gave up. So I'm glad we've got that one. Cool. Thanks for stopping by. Have a good one. Ciao for now. Thank you.